Have you ever heard the faint whisper of the cosmos? For decades, humanity has sought to decipher the most subtle signals of the universe, attempting to capture fragments of reality that are nearly lost in the vast silence of space. These fragments originate from the very events that sculpted the cosmos itself. In this journey of exploration, the concept of the gravitational wave background has emerged as one of the most profound breakthroughs in modern science. Gravitational waves are essentially ripples in the fabric of space-time, generated by the most violent and ancient processes in the universe. They carry a narrative older than the stars, a story not written on parchment but etched into the very foundations of reality. Today, we invite you to step into this cosmic symphony as we trace its journey, the science behind it, and its deep impact on human understanding from the earliest theoretical postulations to the cutting-edge technology that makes their detection possible. In this exploration of the invisible history of our universe, we bridge the gap between Einstein's radical predictions and the modern annals of the gravitational wave background. At its core, gravitational waves are fluctuations in the geometry of space-time. Albert Einstein first predicted their existence in 1916, a direct consequence of his general theory of relativity. These waves propagate through the vacuum at the speed of light, carrying information from cataclysmic cosmic events, such as the collision of neutron stars or the merger of massive black holes, and even the explosive birth of the universe itself. While the first direct detection by the Laser Interferometer Gravitational Wave Observatory, or LIGO, in 2015 marked a monumental leap for astrophysics, those sharp, fleeting signals were merely the tip of a much larger phenomenon. This broader phenomenon is the gravitational wave background, a faint, persistent hum that permeates the entire universe, formed by the superposition of countless individual sources. Unlike the distinct and sudden chirp of a single black hole merger, the background is more like a continuous, ambient vibration of space-time. Imagine a single gravitational wave event as the solitary cry of a bird, while the background is the collective rustle of an entire forest, a chorus of every living thing breathing at once. Within this mysterious hum lie the deepest secrets of the cosmos, offering clues to how galaxies formed, the nature of dark matter, and the very origin of space-time. To understand where this cosmic hum originates, we must look across all scales of the universe. On a fundamental level, gravitational waves are produced whenever massive objects accelerate in an asymmetrical fashion. Picture two celestial bodies locked in an orbital dance, spiraling closer and closer. As they move, they disturb the surrounding space-time, sending out ripples like stones tossed into a still pond. When these objects finally collide, a colossal amount of energy is released as gravitational radiation, sending a powerful tremor through reality. However, the gravitational wave background is not just the result of these dramatic explosions, it is the cumulative echo of billions of such events. In the earliest moments of the universe, quantum fluctuations during a period of rapid expansion known as inflation may have generated primordial gravitational waves. These ancient ripples are like fossils frozen in the fabric of the universe, still resonating today. Furthermore, as galaxies evolved, the frequent mergers of binary black holes and neutron stars across the cosmos added to this collective noise, blurring together into a singular, persistent hum. The challenge of detecting these waves is a feat of both engineering and patience. Gravitational waves distort space-time on a scale so infinitesimal it is almost beyond comprehension. Over a distance of several kilometers, the change is less than a fraction of the width of a single proton. To measure this, scientists use incredibly precise interferometers that employ laser beams to monitor the distance between mirrors. When a wave passes through Earth, it subtly stretches and compresses space-time, shifting the path of the laser and creating a change in the interference pattern. While this method is excellent for capturing sudden, intense signals, extracting the gravitational wave background requires complex statistical analysis to separate the signal from the inherent noise of the instruments. By analyzing the statistical properties of this background, specifically its power spectrum, or how energy is distributed. Ultimately, the gravitational wave background is a gateway to the invisible universe. Traditional astronomy relies on light and electromagnetic radiation, but many cosmic events are too distant, too dim, or obscured by clouds of dust and gas. Gravitational waves, however, interact very weakly with matter. They can pass through entire galaxies and vast dust clouds completely unimpeded, reaching us in their pristine, original state. Through this background, we can observe populations of black holes and neutron stars that are otherwise undetectable. We can trace the history of galaxy formation and test the limits of our physical laws, examining whether general relativity holds true under extreme conditions or if there are hints of quantum gravity. This research is still in its infancy, but the horizon is bright. As our technology advances and our sensitivity increases, we are moving closer to fully hearing the cosmic roar that has been playing in the background of our existence since the beginning of time, turning the silence of space into a rich, data-filled symphony of our universal history. Ground-based gravitational wave detectors are instruments of almost unimaginable sensitivity. They do not merely listen for the ripples of the cosmos, they are equally responsive to the terrestrial world, the subtle tremors of the earth, the rhythmic crashing of distant ocean waves, the rustle of the wind, the rumble of urban traffic, and even the minute fluctuations in atmospheric pressure. To isolate a cosmic signal from this overwhelming sea of noise, scientists must rely on extended periods of observation and a technique known as cross-correlation between multiple detectors. When two instruments, separated by thousands of kilometers, exhibit identical random patterns in certain frequency bands, the likelihood shifts from local interference toward a genuine signal from the gravitational wave background. In the realm of data analysis, researchers construct exhaustive noise models and utilize statistical frameworks such as Bayesian inference. This allows them to evaluate the probability of a signal's existence under various hypotheses, gradually revealing the hidden cosmic hum that lies beneath the cacophony of our planet. The successful detection of this background would represent more than just another validation of general relativity, it would serve as an open invitation to explore entirely new realms of physics. The journey toward detecting gravitational waves is an epic spanning over a century. The concept originated from Albert Einstein's general theory of relativity in the early 20th century, though even Einstein himself initially doubted whether such incredibly faint fluctuations could ever be measured. Nevertheless, the idea captivated generations of physicists, recognizing that if these waves could be captured, humanity would possess a radically new way to observe the most extreme environments in the universe. In the 1960s, Joseph Weber designed the famous resonant bar detectors, often called Weber bars. These massive aluminum cylinders were engineered to vibrate in resonance with passing gravitational waves, a motion so slight that it required the most sensitive electronic instrumentation of the era to detect. Although subsequent experiments failed to replicate his claimed detections and raised serious doubts about the method's reliability, Weber's efforts opened a vital door. He inspired the first serious attempt to build a machine capable of capturing the minute ripples in the fabric of space-time. By the 1970s, the emergence of laser interferometry changed the nature of the quest. Unlike the resonant bars, interferometers use light to measure distance. Laser beams reflect between mirrors at the ends of long vacuum arms, creating interference patterns. Any infinitesimal change in the arm lengths causes the pattern to shift. This concept, championed by pioneers like Rainer Weiss, eventually evolved into the world-renowned LIGO project. In its infancy, the technology faced staggering obstacles. Ground vibrations, temperature fluctuations, thermal noise within the mirrors, and the quantum noise of the laser itself were each capable of drowning out any cosmic signal. For many years, the mission seemed nearly impossible, finding a change in length smaller than the width of an atomic nucleus amidst a world of noise. Yet, researchers persisted, refining suspension systems by hanging mirrors on multi-stage pendulums, isolating the apparatus in ultra-high vacuum chambers, and developing incredibly stable laser sources. By the 80s and 90s, breakthroughs in numerical relativity and computational astrophysics provided the theoretical sheet music for these instruments. Scientists used supercomputers to simulate the collisions of black holes and neutron stars, predicting the specific waveforms these events would produce. With these templates, they could use matched filtering to sift through noisy data for matching patterns, vastly increasing their sensitivity. International collaboration became the final piece of the puzzle. With facilities like LIGO in the United States, Virgo in Europe, and Kagra in Japan sharing data, the entire planet essentially became a unified gravitational wave observatory. In late 2015, LIGO finally captured the first clear gravitational wave event, the merger of two stellar mass black holes. This historic detection confirmed Einstein's century-old prediction and signaled the official birth of gravitational wave astronomy, soon followed by the observation of neutron star collisions and the dawn of multi-messenger astronomy, where gravity and light are studied together. Beyond laser interferometry, a completely different set of tools is helping us explore the gravitational wave background: pulsar timing arrays. Pulsars are the dense remnants of supernova explosions, spinning at incredible speeds and emitting regular pulses of radio waves. To observers on Earth, they act as nature's most precise cosmic clocks. Millisecond pulsars, in particular, rotate hundreds of times per second with remarkable stability, making them ideal natural probes for ultra-low-frequency gravitational waves. As a wave passes through the space-time between Earth and a pulsar, it causes the distance to stretch and contract ever so slightly, leading to minute deviations in the arrival time of the pulses. While it is difficult to distinguish these deviations in a single pulsar, monitoring an array of dozens or even hundreds of pulsars over many years allows scientists to look for correlations. This collective pattern of timing shifts is the signature of a gravitational wave. Background. These arrays are sensitive to frequencies far lower than those detected by ground-based interferometers, making them perfect for observing the slow, powerful dance of supermassive black hole binaries and processes from the very early universe. Major international projects have recently reported signals consistent with these expectations, marking the moment humanity truly began to hear the deep, low-frequency resonance of the distant cosmos. The breakthrough of gravitational wave astronomy began with these distinct, individual events, but they are only pieces of a larger puzzle. If we imagine the gravitational wave background as a vast ocean, then each detected black hole merger is a single splashing wave. These events provide crucial data on the population of sources in the universe, their masses, their spin, and the frequency of their collisions. In some complex environments, such as dense star clusters, binary systems may have eccentric, elliptical orbits rather than perfect circles, leaving unique spectral signatures in the background. Furthermore, when black holes formed from previous mergers collide again, they create a hierarchical process that leaves its own mark on the cosmic hum. By statistically analyzing these events and projecting them across the history of the universe, we can calculate the total background signal we expect to hear. This background is not just a collection of echoes, it is a fundamental test for our understanding of the universe. At the deepest theoretical level, detecting primordial gravitational waves relics from the quantum fluctuations of the inflationary epoch shortly after the Big Bang would allow us to measure the energy scales of the universe's earliest moments. This would not only verify the theory of inflation but would also challenge our fundamental understanding of the origin of space-time itself. Through this persistent cosmic hum, we are moving beyond merely observing the universe, we are learning to read the epic story of its evolution, etched into the very gravity that holds it together. Beyond the standard astrophysical sources, the early universe's phase transitions may have left a significant mark on the gravitational wave background. If such a transition was of the first order, it would have involved the rapid expansion and violent collision of vacuum bubbles, a process capable of etching distinct peaks into the frequency spectrum. Similarly, models involving cosmic strings hypothetical 1-dimensional topological defects in the fabric of space predict that these strings would emit bursts of gravitational radiation as they vibrate, break, or reconnect. The cumulative effect of countless such events would form a background with a highly characteristic spectral signature. More ambitious theories suggest modifications to general relativity itself, such as scalar tensor theories or frameworks introducing additional degrees of freedom for gravity. These modifications could alter the propagation speed, polarization states, and damping mechanisms of gravitational waves, differences that would ultimately manifest in the overall spectrum and angular distribution of the background. Furthermore, certain dark matter candidates, like axion-like particles, might have coupled with electromagnetic or gravitational fields in the early universe, triggering the enhancement or suppression of gravitational waves at specific frequencies. Even the frontiers of quantum gravity, including string theory and loop quantum gravity, suggest that at the smallest scales, the structure of space-time undergoes quantum corrections. This could lead to non-standard polarization modes or high-frequency components in the gravitational wave background. Detecting these deviations would represent our first experimental contact with the boundaries of quantum gravity. Other exotic contributors to this cosmic hum might include the evaporation of primordial black holes. If a large number of these black holes existed in the early universe, their gradual decay via Hawking radiation over billions of years would be accompanied by the release of gravitational waves. Models involving extra dimensions, such as those found in string theory or brane-world cosmologies, suggest that gravitational waves might propagate through higher dimensional space, leaking energy, and altering the spectral features we observe from our four-dimensional perspective. There are even cyclic models of the universe which propose that reality undergoes periodic contractions and bounces rather than a single Big Bang. In such scenarios, gravitational waves from a previous cycle could survive and mingle with the background of our current era. To listen more clearly to these whispers, humanity is designing a new generation of detection technologies. Leading the way are space-based observatories like LISA, planned for the 2030s. This mission will consist of 3 spacecraft forming a massive equilateral triangle with sides spanning millions of kilometers. By operating in the silence of space, far from terrestrial seismic noise and atmospheric interference, LISA will be uniquely positioned to observe the low-frequency signals that ground-based detectors cannot reach, such as those from supermassive black hole mergers, cosmic strings, and primordial ripples. On the ground, projects like the Einstein telescope will utilize an underground triangular layout and cryogenic mirrors to suppress thermal noise, while the Cosmic Explorer aims for arm lengths of tens of kilometers to capture stellar mass binary mergers with unprecedented clarity. The evolution of detection also embraces quantum technologies and international synergy. Methods like the quantum squeezing of light are already reducing uncertainty in our measurements, while future quantum metrology and advanced sensors will continue to push beyond the traditional noise limits of interferometers. In the ultra-low frequency regime, the power of pulsar timing arrays will grow as telescope sensitivities improve and the number of monitored pulsars increases. Large-scale projects like the Square Kilometre Array will provide a much finer sampling of the cosmic background. This research does not exist in isolation but is deeply intertwined with multi-messenger astronomy, connecting gravitational signals with electromagnetic waves, neutrinos, and cosmic rays. For instance, comparing the distribution of quasars with the anisotropies in the gravitational wave background allows us to cross-validate the history of galaxy mergers and black hole growth. We may even find that high-energy cosmic rays or fast radio bursts originate from the same violent environments that generate gravitational waves. By analyzing these signals in tandem, we can witness how matter behaves under extreme conditions and how energy is distributed across the cosmos. Even the phenomenon of gravitational lensing, where massive clusters of galaxies warp the path of passing waves, will provide a new way to map the distribution. Ultimately, the study of the gravitational wave background shakes our worldview at a philosophical level. By capturing ripples from the dawn of time, we are moving the question of our origins from the realm of myth into the domain of observable evidence. We are no longer merely describing a beginning with words, we are listening to its echoes. This background reminds us that the universe is not a static backdrop but a vibrant, oscillating tapestry where every galaxy, black hole, and explosion leaves its own rhythm. It challenges our human-centric perspective, showing us that causality and cosmic evolution operate on timescales far beyond our brief existence. Every ripple we observe likely originated from an ancient, nameless merger that took place long before the Earth was formed. This collective hum represents a grand cosmic harmony, where individual violent events merge into a larger, orderly structure. Whether or not there is an observer, these waves continue to sculpt the fabric of space-time, existing independently of our perception. Yet, it is our active pursuit of understanding our decision to listen to the symphony that gives these signals their meaning. As we bridge the gap between the largest structures of general relativity and the smallest scales of quantum mechanics, we are driven by the profound desire to understand a unified reality. The gravitational wave background serves as a bridge between empirical science and our deepest curiosities, turning our abstract reflections on existence into a tangible, measurable journey toward the ultimate truths of the universe. Supermassive black hole binaries typically form during the monumental mergers of galaxies, where they may spend millions of years or even longer in a slow, inward spiraling dance. During this process, they emit gravitational waves at extremely low frequencies, a regime where pulsar timing arrays are most sensitive. Consequently, these arrays are vital for providing a statistical portrait of the supermassive black hole population across the history of the universe. Under more extreme conditions, black holes might experience close, non-merging encounters along hyperbolic orbits, producing brief but intense bursts of gravitational radiation that leave their own distinct traces in the cosmic background. The physical properties of these black holes, such as their spin and mass ratios, significantly influence the resulting waveforms. For instance, rapidly spinning black holes alter the polarization and frequency structure of the waves, while binaries with unequal masses generate richer harmonic components. These intricate details are ultimately encoded into the overarching spectrum of the gravitational wave background. The environment surrounding these black holes also plays a crucial role. In supermassive systems, accretion disks composed of gas and dust exert dynamical feedback on the binary's orbit, shifting the rhythm of their in-spiral and subtly tuning the gravitational wave signal. Furthermore, if primordial black holes were formed in the early universe, their long history of mergers would contribute a unique layer to this background hum. Some theoretical models even suggest that under the influence of quantum gravity, the event horizon might not be a perfectly smooth structure, potentially giving rise to echoes, a series of gradually decaying ripples that follow the main gravitational pulse. Observing such echoes would fundamentally transform our understanding of the very nature of black holes and the fabric of space-time. Additionally, the interaction between black holes and dark matter halos could leave detectable imprints, as the gravitational influence of dark matter clouds can delicately alter the morphology of the gravitational wave signal. In essence, studying the black hole contribution to the gravitational wave background allows us to use the language of gravity to describe how the most extreme structures in the cosmos are born, grow, and eventually perish. The gravitational wave background serves as a connective tissue for many disparate astrophysical mysteries. By analyzing its integrated spectrum, we can work backward to uncover the true mass distribution of black holes and neutron stars, identifying whether certain mass ranges are vacant or particularly crowded. This data directly informs our understanding of the evolution of massive stars and the underlying mechanisms of supernova explosions. Moreover, this background is intimately linked to the history of star formation. The birth and death of massive stars produce the compact objects that eventually become the sources of gravitational waves. By combining these signals with electromagnetic observations across different cosmic epochs, we can reconstruct the rate of star formation over billions of years, observing the rhythm of the universe as it lights up and fades away. The history of galaxy mergers is similarly echoed in the background, since the growth of supermassive black holes depends on both accretion and mergers. The gravitational wave background reveals just how frequent these galactic collisions truly are. In dense environments like globular clusters or galactic nuclei, the dynamical evolution of compact objects is incredibly rich. The gravitational wave background helps us decipher the true population of these dense stars in such crowded regions. Furthermore, the waves generated by neutron star mergers carry information about the equation of state, which describes how ultra-dense matter behaves under the most extreme pressures imaginable. Precise analysis of these signals allows us to constrain the relationship between pressure and density within a neutron star, providing rare and precious clues for nuclear physics. Even dwarf galaxies, which are often overlooked in traditional surveys, contribute to this collective hum through their own populations of compact binaries. Overall, the gravitational wave background acts as a condensed astrophysical archive, packaging the behaviors of black holes, neutron stars, galaxies, and clusters into a single spectrum of intensity and frequency. As our detection sensitivity continues to improve, this archive will become increasingly clear, allowing us to answer questions through direct observation that were once only accessible through indirect inference. That concludes our journey for today. May you have peaceful dreams and a wonderful day ahead. We will see you in the next episode.